All right, good morning, everyone. It is the behavior of waves. This is the last section on waves that we'll be covering. And so you just want to hang on and take some notes while we go over this. Hopefully it makes some sense to you guys. First thing I want to talk about with behavior of waves is a thing called reflection. All waves reflect, as you can see by the pictures here, there's mirrors and also sunlight reflecting off the water. Reflection occurs when a wave strikes an object and then bounces off of it. All types of waves can be reflected: sound, light, water. These are all ones that are affected by reflection. An echo that you hear is a result of reflecting sound waves. Right? They're reflecting back to you. When waves are reflected, their direction can be predicted. That's how bats use echolocation, and other dolphins use underwater echolocation sonar as well. When the wave is reflected, we can figure out where the sound is coming from. Okay. The law of reflection is this: the angle of incidence is always equal to the angle of reflection. So if you look down here at this picture, notice how here you have the angle of incidence, I, that's just the in arrow, okay? And that reflection, the bounce off, is the R angle. And those two angles are always equal, okay? So if one's coming in at 45 degrees, that means your reflection is also going to lead at 45 degrees from the flat surface. Now that is still the same even if the surface is turned, okay? And that actually will change a few things, but the angle is the reference to the flat surface that it's bouncing off of. Incidence, again, is the beam or angle that strikes the reflecting surface. A reflection, that's the beam that leaves the reflecting surface. Okay? Pretty straightforward stuff with reflecting. Refraction is a little more complicated, but it's still something that we deal with. It's the bending of a wave. It's caused by a change in speed. All right, so the wave speed, we learned that about last time with our lecture, is it travels from one medium to the other. For instance, our pencil over here in that little mug of water, the light that's coming off of that as the light goes into the water changes speeds. That makes it look like the pencil is broken. Okay, so if the medium slows the wave, it bends toward the normal, and the normal is right here, that little dotted line, the surface normal, 90 degrees off of the surface. All right, if it slows it, it bends toward it. So you'll notice right down here, the arrow is being slowed, so it just think of it like when you drop something in the water, you may be throwing it forward, but as soon as it hits the water, that forward velocity kind of stops and it drops straight down into the water. All right, that's the light wave is doing here. All right, so normal again is the 90-degree line to the surface. If the medium speeds up the wave, it bends away from the normal. Excuse me. So there are a few mediums out there, liquid mediums, that actually speed up the wave, and it's pretty cool doing that. I would show you that in class, but I don't have the stuff here at home to do that. So we'll just move on. Diffraction is the most complicated of the different behaviors that wave is. And what diffraction is, it's the bending of a wave around an object. A wave doesn't just stop if it hits an object. It has a tendency to bend around it. If you look at this picture over here, you can see where all these waves are bending around these different land structures out in the water. And as you can see, the water is moving this way. The waves are yet through this aperture, this hole, and between these rocks, the direction of the waves change to go toward the top of the picture. And of course, you can see little reflections, right, as it's kind of bending outward. And we'll talk about that here in a second. Waves can be diffracted also through a narrow opening, a small cove. Looks like there's a lot of chaos out here because all the waves are reflecting off of the other rocks. But if you get away from all that, you notice how there is a definite pattern of waves that are inside this cove, and they ring around. We'll talk about that behavior between the different size of openings, the size of the wavelength. All those things matter. So diffraction and wavelength. How much does a wave bend when it strikes an object or an opening? There are two factors that we need to be aware of. Okay. First factor is the size of the obstacle. All right. If the obstacle is the same size or smaller than the wavelength, remember the wavelength is the one point of a wave to the next point, from either crest to crest, trough to trough, or halfway through. All right. So if the obstacle is the same size or smaller than the wave bends around it. Okay. If the obstacle is much larger, excuse me, not much diffraction happens, but instead there's a shadow. And I have a picture that I'll show you that shadow in a second. Okay? And the size of the obstacle, this is one of the reasons why water breaks and different things that happen in harbors when they make an unnatural area into a harbor, they use huge breaks to stop the waves, and that causes the shadow from the water. We'll look at a picture that shows that here in a second. The second factor is the size of the opening. The closer the size of the opening to the wavelength, the greater the amount of diffraction. So the closer you have, if the opening is the exact same wavelength, the distance of the wavelength, there is a huge amount of diffraction. Again, I have some pictures here showing that. So here are some diffractions around an object. You'll notice here that the object here, up here, is much larger than the wavelength, and so it shows how it bends around. So notice the waves over here continue on unaffected, and yet there is a reflection, right? A little shadow that happens over here. We call that shadow. Again, here is a large obstacle with waves going on both sides, and then again, here's a small shadow of protected area. Okay. And if you ever wonder why circular patterns happen in the sand around posts or piers that are out in the water when the tide goes out, here's the reason for it. As waves come in, they are reflected in all directions around that post, so it makes a little ripple effect around the post. Pretty interesting, pretty cool patterns that can happen in structures in the water. Here are some different openings that we talked about: a large opening, a small opening. Okay? So if they have a large aperture, notice how there's not much diffraction. There's not much change, right, in where the waves are going. But over here we have a very small hole, small aperture, and notice how there is a huge ripple effect, this huge pattern that spreads out because of that. If you have a large wavelength, very big waves, in a large opening, you have very high levels of diffraction as well, which is why most harbors have typically very small openings, and then they will actually have the boats turn, and most of the docking will take place away from the diffraction. So they'll they'll have a 90-degree turn away from the opening to go out to sea to have a very well protected harbor. All right, here is a great picture that shows all kinds of diffraction. Notice over here in these small little islands off the right side of the picture, there is a kind of this ring reflection and how far out these patterns actually go. It's pretty cool being up in an airplane over the water, and you can see these different patterns of waves. And this also explains why certain areas have nice large waves for surfing. And they can be protected from the wind, and you can still enjoy a large wave coming in to surf. You got to realize how large these waves are. These are buildings down here. Okay, these little dots. So these waves coming in are very large in wavelength. Okay, big waves. All right, whoops. All right, interference. The next thing we talk about is interference. Interference is the process of two or more waves overlapping and combining to form a new wave. Okay. Interference is really cool, and this explains how both things happen with, say, noise-canceling headphones, as well as like concert halls, opera houses, theaters, how they use acoustics to amplify the speaking voice. I know several times when I was over in Europe, went to some very old cathedrals, and you can be sitting up in the balcony at the far back of the sanctuary, and someone can be just talking with a normal voice down at the other end, down at the altar where the priest or pastor would be saying something, and they can speak in a normal voice, and because of the interference that happens, you can actually hear the person very, very far away because of how the acoustics are set up inside the building. The acoustics is the study of waves. I don't know if I put that in this one or not, but that's what acoustics are. They're the study of waves. So in interference, you have the process of two or more waves overlapping and combining to form a new wave. So the new wave exists only when the two original waves continue to overlap. And interference can be either destructive or constructive. We'll talk about both of those here. So in here, this shows how two waves, when they overlap together, the same peaks or the crests are together and the troughs are together. Notice how you have an amplified wave down at the bottom. It's twice as tall. Yet when they're exactly opposite of each other, there is no wave. All right, and this is what destructive interference does, which is how you noise-canceling headphones work. Okay? So here's a picture again, a non-moving one that shows how constructive interference works. If your peaks and your troughs are in sync, you have constructive interference, and it doubles the size. It adds the two components, A and B. Notice over here, destructive, all right, their trough and the crest, and sometimes I say peak instead of crest, but the trough and the crest they cancel each other out. And so that results in a no wave. The wave gets canceled out, okay? Constructive interference, again, is when waves add together to make a larger wave. The amplitude of the new wave is the sum of the two waves. You just add them together. So if it's a sound wave, the sound increases. And this is how, again, acoustical correct halls, concert halls, theaters, opera houses, things of those nature, that is how they use constructive interference to make a louder sound, just by having a interference, a positive interference, constructive interference. Destructive interference is when the waves subtract from each other and make a smaller wave. The amplitude of the new wave is the difference of the two waves. And again, if it's a sound wave, then the sound decreases. And if you ever put on a pair of noise canceling headphones, when you first put them on, you hear that, and then it gets really quiet. That's the microphone and basically the processor that works there that's interpreting all of the different wavelengths of sound that are around you. It's basically creating the destructive pattern, the exact opposite pattern of those waves to cancel out that noise. So that's that first little hiss, the hush sound that when you put on a pair of active noise activated canceling headphones. Okay. Standing waves. So a standing wave is pretty cool. It's a special type of wave pattern. If we were doing this in a lab in class, we actually make some standing waves. And it is a special type of wave pattern when waves equal the wavelength and amplitude as the wave travels in opposite directions. And you can do a standing wave if you have two of you with the jump rope, and you have one person start making a transverse wave, shaking it up and down, shaking it up and down. All of a sudden, you'll see this point where it looks like the wave is almost standing still because everything is in harmony. All right, and that is when your wavelength and amplitude are equal to each other in opposite directions. And so you'll notice over here, the nodes are basically the different places that there is movement. So this would be like a single jump rope. You're just trying for your friend to come over, but then these lower ones, mode 4, 3, 4, and 5, are when you're shaking it up and down and you get that harmony. And then it looks like the rope is just doing that in constant movement. It's pretty cool. You can practice that if you want to. It's a lot of fun looking at standing waves. And a node, we call those nodes where the waves always cancel each other out. Right? So that's what, there's no constant ripple along this rope anymore. It's a rhythmic pattern. Right? And we would do this in class. We got some rope and some stuff like that where we would practice doing standing waves. Standing waves are actually what are made by stringed instruments. When you strum a guitar string, a violin, anything that has a string on it, if you actually watch, you'll notice when you strum it, it looks like it's kind of vibrating and moving, but it doesn't. It has this rhythm to it if you look at it very closely, and then the more it vibrates, the higher the tone. Okay. Last thing we'll talk about is resonance. What is resonance? Resonance is the process by which an object is made to vibrate by absorbing energy at its natural frequency. So everything in nature, everything that we have around us, has a natural frequency that it vibrates at. Remember, even solids have atoms that are vibrating inside of it. And if you can match the vibration of those atoms in a solid object, you can actually cause it to absorb energy. Okay? And if you give it enough energy, as this glass in this picture shows, the glass will break. And I don't know if you've ever seen people do this with their voices. Some singers are able to match the frequency of an object, and they can get it to vibrate and make glass break with their voice. They're not doing it with how loud their voice is. They're doing it with the frequency that their voice is, which is how the concept of all sonic weaponry and all that kind of stuff works for stunning and things of that nature. But anyways, that is our presentation for today. Hopefully, again, you were able to get some information out of here. This is the last presentation that you'll have from me this year. So I hope you all enjoy it. And if you have any questions, just shoot me an email. Thanks.